Okay, so we're going to continue with some of the other gas laws. The next one is called Charles's Law. And Charles's Law, so by the way, when we talk about the names of the different gas laws, it's great that you know what the names are, but the most important thing is that you know what the parameters are that we're actually trying to relate. Okay, so Charles' Law relates the volume and the temperature. So this is a V and T relationship. And again, if we're looking just at the relationship between volume and temperature, we're going to keep the other two parameters. So we're going to keep N, the amount, and we're going to keep pressure constant. And when we have these conditions, what we actually find is that V and T are directly proportional to each other. So as opposed to an inverse relationship that we saw with Boyle's law, the PV relationship, in a direct relationship, what we find is that if the temperature, for example, increases, if V is directly proportional to it, that means the V volume should also increase. And also, the opposite would be true. If the temperature decreases, we would find that the volume decreases as well. And we have here an example where this is illustrated. We have a balloon at room temperature, for example. There's a volume that the gas occupies in it, the volume of the balloon. If we put some, this looks like liquid nitrogen on there, which is very, very, very cold. Obviously, here the temperature now decreases. And as a result, the volume of the balloon decreases as well, right? So that's a very simple illustration of Charles's law. And again, just like with Boyle's law, the PV relationship, the way that we express this mathematically in a way that is going to be useful to us, we can relate initial and final conditions, just like we did previously. And what we can say now is V1 over T1 is equal to V2 over T2, right? Because V over T, that relationship, is now equal to a constant. We can refer to that constant, which, any sort of symbol. And because this relationship holds true, we can make this equality hold true as well. So just like with the previous example, right, in a gas law problem, we have to extract the relevant information, list it, and figure out the gas law that's going to be most appropriate. There is one thing to consider, one additional thing to consider here, though, and that is now we're getting into the use, we're seeing temperature. And we did talk about temperature as one of the parameters. And the key thing about temperature here is that your temperatures must be in Kelvin. Okay, before you start plugging your numbers in into your equation, go ahead and convert it to Kelvin first, and that way you won't forget to do it later on. So it's the same idea as Boyle's law, right? We're relating two variables or two parameters, and then we're based on what information we're giving in the problem. There's one unknown that we need to solve for in this equality, in this equation. Rearrange the equation to solve for that particular unknown, and then simply substitute our values to solve for that unknown. Based on Charles' law, what we can also do is, we can plot differences or changes in the volume of a sample as we increase the temperature, for instance, right? So as temperature goes up, the volume increases as well. So we see that these slopes here for these different gases sloping upwards. What we could also do is we can extrapolate these numbers backwards, going this way for each of these three curves, and we can actually we can figure out the temperature at which the volume of a gas is 0. In other words, the gas doesn't occupy any space whatsoever, and that would be the temperature at which the gas particles just slow down completely or stop completely. And all of these lines here will intersect at that very important temperature, negative 273 Celsius. If you recall, that is known as absolute zero. right, and that corresponds to 0 Kelvin, we could actually determine that experimentally just by collecting a bunch of data points, volumes at different temperatures. The temperatures can be, normal room temperatures, collect several of them, and then just simply extrapolate, get a line of best fit, extrapolate backwards, and wherever the volume equals 0, whatever temperature that corresponds to, that is actually absolute 0. All right, so another law that we're going to see is sometimes referred to as Amonton's law. And the Amonton's law is the pressure-temperature relationship. And if we're looking at the relationship between pressure and temperature, again, here we're going to keep the other two parameters, N and volume, constant. Okay, and the relationship between pressure and temperature here is also a direct relationship. So P and T are directly related to each other. So again, what this means is as temperature goes up for gas, the pressure is going to increase as well. Right? You can think about it intuitively. As you increase the temperature, the average kinetic energy increases. The particles are going to hit the walls of the container with a greater speed and greater frequency. As a result, the pressure goes up. And then the opposite would be true as well. As temperature goes down, the pressure is going to go down. Remember, your temperature must be in Kelvin. Whatever you see T in your gas law problems, you need to make sure that they are in Kelvin. And just like the VT relationship, which was also a directly proportional relationship, we can relate P and T in a similar way. We can say the pressure over the temperature is going to be a constant. Okay, and then the way that we make this useful to us is we can relate now initial and final conditions, just like we did previously. We can say P1 over T1 is equal to P2 over T2. Right, and by the way, this relationship is one of the reasons why you don't heat. If you have a sealed canister or sealed cylinder of a gas, you don't heat it up because you have a constant volume. You heat up a cylinder of a gas, the pressure is going to increase until eventually that container can actually explode as a result of the increase in pressure. So PT relationship, a directly proportional one between pressure and temperature when we keep the N amount and volume constant. Okay, so we've seen so far 3 gas laws, and we've been able to now incorporate pressure, volume, and temperature into each of those gas laws. We haven't seen N, the amount, just yet. And we're going to take a look at N in Avogadro's law. And we've seen Avogadro before in terms of Avogadro's number in a mole. This is another place where his influence is quite apparent. And in Avogadro's law, what we are relating is the amount. So the amount now is N and volume V. So if we're looking at Avogadro's law, this is the Vn relationship. And if we're just looking at these two, we're going to keep the other two parameters constant. We're going to keep pressure constant. We're going to keep temperature constant. And what we find here is that V and N are also directly related. Okay, and simply put, what this means is as N increases, as the number of moles of a gas increases, the volume that the gas occupies is going to increase as well. And that should make intuitive sense, right? The more of something that you have, the more space it's going to occupy, right? And that is what Avogadro's law is essentially saying. So just like with the previous 2 gas laws we looked at where there were direct relationships, we can make some mathematical equations to relate these two. We can say the volume over the amount, N, is equal to a constant value. And then when we relate this now to our initial and final conditions, we can say that V1 over N1 should be equal to V2 over N2, right? And again, this is the form that is going to be useful to us when we start doing our calculations down the road. Again, in your problem, in most cases, right, you're provided with 3 of these things. There's one unknown. We can then rearrange the equation to solve for that one unknown.